How does thermodynamics limit energy efficiency? Imagine trying to squeeze every bit of energy out of a fuel or heat source, only to find that some always slips away as unusable heat. That's where thermodynamics comes into play, setting the rules for how efficiently we can convert energy. It might seem like magic, but it's all about the laws of physics that govern energy and heat transfer. These laws tell us that no process can be perfectly efficient, no matter how clever the design. The second law of thermodynamics is the main reason. It states that in any energy conversion, disorder or entropy increases. This means some energy always disperses as heat that can't be turned into useful work. Think of it like trying to clean a messy room. No matter how much effort you put in, some clutter remains. This increase in entropy limits how much useful energy we can get from a system. Now, the idea of Carnot efficiency helps us understand the maximum possible efficiency for heat engines. These engines use heat from a hot source to do work, like turning turbines in a power plant. The maximum efficiency depends on the temperature difference between the hot source and the cold sink. The bigger the temperature gap, the more efficient the engine could theoretically be. But in real life, it's impossible to reach this ideal because of inevitable losses. Things like friction in moving parts, turbulence, and heat transfer limitations all reduce actual efficiency. For example, in a coal power plant, burning coal produces high-temperature steam that spins turbines. But some heat is lost when the steam cools down and is rejected to the environment. This heat loss means the plant can never reach the maximum efficiency predicted by the Carnot limit. Materials also play a role. Engines and systems have temperature limits they can handle without breaking down. These constraints prevent us from operating at the ideal temperatures needed for maximum efficiency. Even solar panels face thermodynamic limits. They can't convert all sunlight into electricity because some photons don't have enough energy, and excess energy turns into heat instead. Multi-junction solar cells improve this, but they still can't surpass the fundamental thermodynamic boundaries. In heat transfer and energy conservation, these principles show us why we can't turn all input energy into useful work. They reminded us that some energy will always be lost, whether as heat or friction. Understanding these limits helps engineers design better systems that minimize waste and operate closer to their maximum potential. But it's important to remember that these laws are fixed. They set the ultimate boundaries we cannot cross. So, in simple terms, thermodynamics limits energy efficiency because of the natural increase in disorder and the temperature differences we can create. Real-world factors like mechanical losses, heat transfer issues, and material limits further reduce what we can achieve. These laws guide us in making smarter, more efficient energy systems, but they also reminded us that perfection is impossible.